Let's talk about matrix correction procedures. The matrix correction is what turns effectively the peak height, which is a measurement of X-ray intensity. Remember, we directly measure X-rays. We're not counting atoms, we're measuring X-rays. And we want to turn these X-ray measurements into weight percent, into atoms. The problem is, not every atom produces an X-ray. Not every X-ray that is produced makes it to our detector. So we need to do a lot of calculations to get between the measured X-ray intensity to the corrected weight percent. That correction is what the matrix correction does. It's also traditionally called the ZAF correction. The first part of the matrix correction is the background subtraction. You look at that spectrum there. I got iron, I got silicon. If you went to measure the iron peak, you'd measure the peak height there. That's fine. People would say that's how high the iron peak is. But I'm only interested in characteristic iron K-alpha X-rays caused by inner shell ionisation of an iron atom. Unfortunately, I also have present continuum X-rays. And remember, it's called a continuum spectrum because it's got a continuous energy between basically 0 to the Dwayne-Hunt limit where any energy is possible. And so it's quite possible to have a continuum 6.4 keV X-ray. However, a continuum 6.4 keV is not an iron K-alpha X-ray, which is also 6.4. They have the same energy, but they have a different source. One's continuum, one's characteristic. We need to separate that. So what we do is we measure the peak above background. I measure the continuum X-rays to the left of the peak and the continuum X-rays to the right of the peak, and then I calculate the average continuum under the peak, and then I subtract that from the total peak height. And that's called the peak above background. And that's it there. That's the peak above background, and that is the first step in quantification, to remove the continuum X-rays. When you're doing standardless quant on an SEM with an EDS detector, you just push the button, it all happens. However, you just assume it does it right, and mostly it does it very good. On the microprobe, we have a lot more control over how we're going to measure the background. The important thing is the continuum X-ray spectrum is non-zero. It exists. So often the question is, how small amount of material can I measure? And that's basically the detection limit. It's not really a function of the SEM or the detector, it's a function of the continuum produced by your specimen. The denser the specimen, the higher the KV, the more continuum you're going to get. But it's really a specimen density argument. Often when you're calculating detection limits, the minimum amount you can measure, it's all about how big is the continuum. Dense material has, high Z material has more continuum X-rays and worse detection limits. So let's talk about the matrix correction. The first matrix correction is called the Z correction. This is the atomic number correction, Z the atomic number. In actual fact, I like to think of it as a volume correction. If you look at a 20 kV beam hitting your specimen, as you can see on the left, the initial energy, the landing energy of the beam is 20 keV. Each electron has 20 keV in energy. Now, right at the bottom here is the limit of the interaction volume. What is the energy of an electron at the end of the volume? Well, it's 0 eV. Because if it had more energy, it would keep on moving. So as the electron penetrates, it loses energy by inelastic events, and it starts as 20 keV, but it ends up as 0 eV. By the way, I'm using 20 keV as an example. Of course, if your SEM is operating at 10 keV, then its starting energy will be 10 keV, but it's the accelerating voltage. So as the electrons penetrate, they're losing energy. They look a bit like, you can assume, like an onion cut in half with all those layers. Let's look at something like this. We have a specimen, one material that contains silicon K-alpha 1.7, and it contains iron K-alpha 6.4 keV. Obviously, because the beam is losing energy, once it goes past that energy, it will stop producing that X-ray. So iron, which requires the most energy, is going to be produced over a smaller volume than silicon. Silicon, which is a weaker X-ray, lower energy, will be produced over a larger volume. This is where errors often happen in analysis. People just assume that the material is being analysed evenly over the whole volume, when in actual fact, it might be one material, but you're only counting iron atoms in a smaller volume and silicon atoms in a bigger volume. That's one of the reasons you can't just straight away directly compare peak heights, because each element has its own unique volume. And don't forget it's a volume. If you remember, volume is r cubed. So a small change in radius, in distance, can actually translate, because it's a cubic function, into a large change in volume. It can be quite significant. So that's the volume effect. Each element, each Z, has its own unique X-ray generation volume. The second effect is called the A effect, or the X-ray absorption effect. Just because an X-ray is created doesn't mean it's going to make it out of the sample to hit our detector. The only ones we count are the ones that hit our detector. Basically, the weaker the X-ray, the more they get absorbed by the surrounding material, and also the deeper the X-ray, the more material it has to pass through and the more it gets absorbed. So if you look here, again, my stronger iron X-ray, any iron X-rays near the surface, very high probability of making it out. Deeper iron X-rays, less chance of making it out. But at least they're strong X-rays. You go to a weaker X-ray like silicon, near the surface again, most of them will make it out. But a deep silicon X-ray, very low chance of actually escaping the specimen. You can look here, my detector is off to the right. It's called the takeoff angle. We know exactly where it is because we always set it up to the same geometry, because you're always working at the correct working distance. And you can see X-rays produced near the surface pass through a small amount of material, whereas X-rays deep pass through a large amount of material and have a higher chance of probability. So for each little depth slice, I need to calculate the probability of each X-ray making it out of the specimen. That's an absorption calculation. Again, it's a function of the accelerating voltage, the X-rays, the matrix, and the sample shape. For the absorption correction to work, for us to get the mathematics right, the people who did the software and did the mathematics and the calculations originally had to make some assumptions. So the assumption is that your specimen is flat, homogeneous, void-free, and beam stable. Why? Because if you look at a specimen that isn't flat, just say you've got this small ridge here, this mountain, this X-ray is passing through extra material on the right than the X-ray on the left is not passing through. The X-ray on the right is being absorbed more. But we don't know that because we just assume it's flat. And we can't calculate any given shape and size. It's just too difficult. So the assumption is it's flat and that this absorption doesn't exist. So if you have topography, you're going to have different absorption. The other thing is porosity. If these are pores or void space, no material there, when the X-ray passes through the voids, it's not being absorbed. So here, with these mountains, the absorption correction is not correct because there's more absorption happening in the specimen than we can account for. With the voids, again, the software doesn't know there's voids in the specimen, so it's passing through bits of material where it's not being absorbed and we don't know it. So here, the absorption correction is giving too much correction. Here, it's not correcting enough. So under-corrected for absorption, over-corrected for absorption. They're the two issues. And the final correction is the fluorescence correction. High-energy X-rays can sacrifice themselves to produce low-energy X-rays. So again, we're just choosing some random elements. Iron K-off at 6.4, silicon K-off at 1.7. This is an artificial example. It probably wouldn't happen much in real life. So for example, assume you've got, in the middle of the interaction volume, you've got an iron atom. And that iron atom is producing an iron K-alpha X-ray at 6.4 keV. On the way out of the material, it encounters a silicon atom. And one of the things it could do, it's a probability thing. Everything at the atomic level is about probability. One of the things it could do is the iron K-alpha at 6.4 can ionize a silicon atom, inner shell ionization, and that silicon atom can produce a silicon K-alpha at 1.7. So that iron K-alpha turns into a silicon K-alpha. But we have leftover energy. What do we do with that leftover energy? We do mathematics. We produce a second X-ray photon, which has the energy of 6.4 minus 1.7, a 4.7 keV X-ray. These are fluorescence effects. We don't really care too much about the other X-ray, as long as we know it. If it's false and we ignore it, we've got no problem. We're sacrificing iron intensity to increase silicon intensity. So the iron to silicon ratio is wrong. We've got to calculate that. This was first noticed with stainless steels. Iron, chrome, nickel are all very close to each other in the periodic table, and they tended to stimulate each other in certain concentrations. So again, we can calculate all that. And that's called the matrix correction. I'm not going to take you into mathematics of a ZAF correction, but basically all ZAF corrections are a function of the accelerating voltage, the X-rays we're measuring, the material, and the shape of the specimen. When I come to the shape or the topology of the specimen, basically I have to make the assumption that it's stable, flat, homogeneous, void-free. I've just got to make that assumption. So you have to give me a flat specimen. You don't have to, but if you want to do accurate quantification, you do. If you've got a rough specimen, it's much more difficult to accurately quantify, and the big issue is it's probably got some errors in there, but I have no idea what those errors are. So I can't tell you whether it's high or low and which elements and by how much. All you can do is a good job or a bad job in X-ray analysis. Here's a typical specimen I've seen where I've got, a general matrix, voids, and little nanoparticles in it. Because don't forget, we do analysis at the micron scale. Unfortunately, even though that specimen is very easy to describe in terms of what makes it up, void spaces, nanoparticles, average size, predicted composition, there's no one micron region I can analyse that gives me the answer. If I analyse this micron region, I get no copper. If I analyse with a copper particle in it, even the same amount of copper, if it's deep, it gets heavily absorbed and I get low copper concentrations. If it's near the surface, I get higher copper concentrations. It's impossible. I need the material to be one material and homogeneous over that whole analytical volume. Otherwise, I can't do accurate analysis. I've just talked you through, quite quickly really, the ZAF correction. A volume correction, Z, an absorption correction, A, and a fluorescence correction, F. I'm not going to take you through the mathematics, and there's various mathematical ways of doing this, and they have various names. They all need certain input from you. The accelerating voltage, the X-rays you're interested in, that's why you need to label the X-rays and remove labels that aren't there. You need to know the matrix and the shape of the materials. Well, the shape is easy, it's flat. The kV is easy, it's the accelerating voltage of the microscope. The X-rays are what we label. That's a direct input into the ZAF correction. The final input data it needs from you is the material. What are you analysing? It needs to know the actual composition of your material so it can do the absorption cross-section. When an X-ray is travelling through a material and being absorbed, it needs to know what material it's travelling through. Stop and think for a second. That's actually a big problem, because in order to do analysis of an unknown material, you first need to know what the material is. So how do we get around that problem? And again, in standardless quant where you just push the button, this is all done behind the scenes. But on the microprobe, we have better control, which leads to better accuracy, and also a huge amount of time being used up. We do this manually. What we do on a microprobe, and you can do this on an SEM with an EDS detector easy enough, and I've seen some good work done. First, rather than put your specimen in the machine, you got to calibrate off the elements you're interested in. So you put pure reference materials in there. For metals, I use pure metals. If I'm doing geology work, I tend to use pure oxides. There's a rule in standards, you match like with like. Metals for metals, oxides for oxides. Let's pretend we're doing metal analysis. So I first put in there some standard reference materials, pure chromium, pure nickel, pure iron. I find the peaks I'm interested in, I find the peak position, and then I measure how high that peak is. Peak above background, background subtraction, in counts per second. So it doesn't really matter how long I measure for, I get a peak height in counts per second. I then go to my unknown material. First, I've done qualitative analysis on this just to identify the elements present, and that's the standards I run. And then I go back to the elements of interest and I measure how high the peak is in my unknown material. And I'll give you some example here. 100% chrome, this is just made up numbers. It's just to show you the workflow rather than some real work. Maybe pure chromium has 10,000 counts per second. On my unknown material, I get 2,000 counts per second. So straight up, that says I got roughly 20% chromium. You always compare the same element peak in your unknown to the same element peak in your reference material. That's the peaks you compare. I don't compare different elements amongst my unknown. I compare the same elements unknown to reference. And then I do the same with nickel and the same with iron, and I make a first order estimate of what the composition of my material is. Again, I just made these numbers up. But what I did see is my total was wrong. My total should be 100%, but of course my total is either high or low. Why is that? Well, because I haven't done any of the ZAF correction, and I can't do any of the ZAF correction because I don't know what the material is. But I just normalize this, assume that that is my material, and I put that first order estimate into my ZAF correction. And that will produce a second order estimate. That's more accurate. And then that, via iteration, is fed back into the ZAF correction, and I got a third estimate. And I just keep on going, feeding the last answer back into the ZAF correction until it homes in on a final analysis. It's usually pretty quick. It happens in a fraction of a second, and for you, it happens behind the scene, but the measuring of your reference material is critical here. And that is how we really do analysis from first principles. Some of you will be joining me on the microprobe, and my colleague Ying Yu. We will be running calibration standards for your materials. It will be very time consuming, of the order of about a half hour per element on standards before we even look at your specimen. And a standard geological run might be 12 elements. That's 6 hours of calibration before I look at your geological specimen. But that's what you have to do to get good quality results. Let's talk about geology. I said we try not to measure weak or low energy X-rays like carbon, nitrogen and oxygen. They're not the best X-rays to measure. Yet geological silicates are obviously full of oxygen. So what do? Well, generally, if I have to, I measure it directly. I can do that. I try to avoid measuring it directly. I basically know that aluminium is in the form of Al2O3. Silicon is in the form of SiO2. And I measure the heavy elements and I calculate oxygen via their standard valence, their known oxide end members. So that's a very nice way of calculating oxygen, and it works very well. It begins to fail when you've got something like iron, which can have a 2+ or a 3+ state. Is iron FeO or Fe2O3? Generally, you'll find if you do it one way, you get low totals, the other way, high totals. So you sort of work out the Fe2+ to the Fe3+ ratio by using software, which is usually in the geology department, where it balances out the ratios to get 100%. That works quite well because I've only got one element that has multiple valence states. But if you add a second element, say manganese, that also has multiple valence states there, it becomes a very, very difficult problem to solve. Well, I'd say almost impossible. So what we then do is, when we have multiple elements with multiple valence states, we just directly measure the oxygen X-ray. In the old days, it was hard to do on EDS, but now both on EDS with an SEM or on WDS with a probe, we can do oxygen directly. I'll talk more about the detectors later. Just a quick little by the way, accuracy and reproducibility. Reproducibility is how much can I reproduce that answer. The answer can still be very wrong, but reproducible. Accuracy is how close my measured answer is to the reality of the situation. Basically, that summarises it there. That's meant to represent a target. There's a bullseye. The bullseye is the right answer. Your deviation from the bullseye is your accuracy. That's your systematic error. If you did the measurement again and again and again, how tight that measurement groups is your statistical error, and that's your reproducibility. X-rays follow Poisson statistics. N X-rays, N being the number of X-rays, has an error of root N, plus or minus root N. Basically, multiple measurements gives reproducibility. How close I am to reality is I need what's called a secondary standard. I need another material that I didn't calibrate on, but I know what the answer is, and it's very close to what my material is. I then analyse that and see how close I am to getting the right answer. Good quality microanalysis is verifying the system works, and it's having a vast selection of reference materials and standards behind you, and you can spend significant amount of time not looking at your specimen, rather calibrating on one set of reference materials and checking your calibration on another set of reference materials before finally looking at your material. Most people just do standardless quantum on EDS and push the button, and that's okay, but I want you to know what's happening in the background for you and how much effort is in taking it to the next level. I'd like to talk to you about X-ray mapping. An X-ray map is producing an image of the specimen, not using the electron signal, but using the X-ray signal. We all know that we can produce an X-ray spectrum, and each one of those peaks, in general, the major peaks, corresponds to a major element of interest. What you can do in X-ray mapping is you label your specimen with the major peaks of interest, and that sets up a window, or an ROI, a region of interest, which you can adjust the width to. But basically, any X-ray that appears within that window is used as a count to map intensity, just like you would use the secondary electron detector to give you an intensity of the secondary signal back. Usually, because there's different peaks, we can do multiple parts of the spectrum, and we'll give each part its own colour. For example, you can raster your specimen, you can look at the secondary electron detector, and that is an SE image. Or you can look at the backscatter detector, that's a BSE image. But over the same raster, you can also look at different regions in your X-ray spectrum, and that produces an X-ray image, which we often refer to as an X-ray map. We normally give it a false colour. Here's one we did earlier. This is a granite, so a standard geological silicate at 20 kV to stimulate lots of X-rays, and a heavy spot size, 67 out of 100, which 100 being big. So we're really working hard on this machine, and we're also putting a lot of energy into this specimen, but it's a geological silicate, it can handle it. That red image on your right is the image of calcium K alpha, and basically where you see red, you see calcium. If the red is stronger, you're seeing more calcium. You can, of course, give different elements their own colour, and you produce a combination map. And here's the granite again, and we've got red is calcium, green is iron, and blue is silicon. And we can look here, this big red crystal is an apatite crystal. It's a calcium phosphate. I'm not seeing the phosphorus because I only labelled 3 elements, and phosphorus wasn't one of them. The blue, to the bottom right-hand corner, that's quartz, silicon oxide. So we can see those big quartz crystals. And this big green thing to the top right, that is hematite, iron oxide. So I've got iron oxide, silicon oxide, and a calcium phosphate. They're very big, strong crystals with significant amount of the elements of interest in them, and it produces a very strong map. To the left, we've got a much more complex mineral. That's a biotite, which is a sheet silicate, and it contains different elements in different proportions. And as you can see, the colours overlap and produce other colours. If you look at the backscatter picture to the left, you can see there's very fine grain structure in this biotite. When you look at the X-ray map, you can't see that fine structure nearly as well. That's because of the interaction volume. Right at the beginning, I told you backscatters might come from 100 or 200 nanometers, whereas X-rays come from 1 or 2 microns. The X-ray interaction volume is bigger, and because of that, the spot size, the effective spot size, not the electron beam, but where the information is coming from on the specimen is bigger, which means the resolution is lower. The signal, in many respects on a bulk specimen, dictates the resolution possible. KV2, matrix as well, but the signal has big input. This is the same specimen, different resolution. One gives a nice picture with Z contrast, the other gives elemental information. I have some considerations for mapping I'd just like to warn you about. One is a geometrical consideration. I think there's a limited range over where mapping is appropriate in general circumstances. If you're doing a low mag map, the beam is moving quite a distance. If your X-ray detector is here, the X-ray detector is to get the electron beam in the centre, the X-rays from there. When you're moving all the way there and all the way there, the X-rays from the extreme, it's not as easy for them to hit the detector. And because of that, at low magnifications, you tend to see the intensity fall off at the edge of the map, even though the chemistry might be identical. The other issue is the interaction volume is 1 or 2 microns. So I did some example here. I did an SEM at 15 kV, 10 millimeters working distance, 5,000 times magnification. That is very reasonable setup for any SEM. The field of view from the left of the screen to the right of the screen was 24 microns. If I just assumed a simple map of 250 by 250 pixels, that means each pixel on the map is roughly 0.1 of a micron. Yet the interaction volume is 1 or 2 microns. That's why the map looks fuzzy, because the interaction volume is bigger than the step size once you get a few thousand times magnification. I really say maps work best above 100 times and below 1,000 times. That's their sweet spot. The further below 100 you get and the more thousands you get, the more likely the map isn't going to produce the results you're after. Generally, I think maps have poor detection limits. The reason is, with a certain accelerating voltage, a certain beam current, I might get 30,000 counts per second on my X-ray detector. If I'm doing a point analysis, where I'm just dropping the beam on a crystal to analyse it, and I may count for something like 20 seconds, that's quite reasonable, that spectrum will have 600,000 X-rays in it. Unfortunately, if I'm doing a large map, say 1,000 by 1,000 pixels, if I pause 20 seconds at each pixel, it would take days to do that map. So what I need to do is I need to be a lot faster. I usually have less pixels and I usually pause at each pixel for a lot shorter time. Say 2 milliseconds might be quite typical. So 2 milliseconds, 2 thousandths of a second, same detector set up for 30,000 counts per second, I'm only getting 60 X-rays total in that spectrum. And because I've got so few X-rays, I've got poor detection limits. So X-ray maps, unless they're done for a large amount of time, and by a large amount of time I'm talking days here, they tend to be only good at showing big changes in the chemistry or the elemental composition. It's harder for them to show small changes. And if they are, you need to usually measure for much, much, much longer. Don't forget, you're now measuring an area, so it's R squared. So to double the pixel density, it's 4 times as long. Here's another example that you've got to make sure you pay attention to. It's not all X-ray maps, some do, some don't, background subtract. Some do it automatically, some you have to use software, some you have to do it manually. Consider the specimen on the left. It's a resin block, so organic material with a bit of lead in it and a bit of quartz in it, SiO2. There is no iron in my specimen, but just say I map for iron. If I don't background subtract, I'll produce a beautiful iron map like you'll see on the right. And it looks like I've got iron there, and it looks like I'm seeing changes in iron concentration. But what I've done is that's a map of the bremsstrahlen, the continuum radiation. The greater the density of the material, the more continuum X-rays are produced. Here's an example. Each one of the spectrums, the silicon, the resin, and the lead, none of them have an iron peak in it, but they got different height of continuum, and the mapping software just automatically scales from the lowest number to the highest number, and it looks like I've got a map. It's not an iron map, it's a density map, or continuum map is a better description. You can correct for that, but you've got to background subtract. Some software does it automatically. In some of the older software, I would map an element that wasn't present. That's my continuum map, and then I would subtract that continuum map from my real maps. Just be aware that when mapping, you can create pictures that don't represent reality. The other thing is, be aware of non-flat specimens if you're trying to do some sort of image analysis on it. When the beam hits the specimen facing the detector, I get X-rays that hit the detector. When the beam hits the specimen on the side away from the detector, it does produce X-rays, but they don't make it to the detector. Here's a good example. This is some mineral sand that's rough. If you look here, you can see 3 nice mineral grains in backscatter. Yet, if you look at the picture here, the shape of the grains has changed. And what I'm seeing is a big shadow region. My detector is obviously to my bottom right, and this spherical particle here is shadowing the other 2 particles and changing their shape. This next section is called Specimen Limitations and Considerations. It's more of a grab bag of a few points that I need to make to the average user, because I see this mistake crop up again and again and again. Not by everyone, but by some people. So I think one of the ways forward in X-ray analysis is to make sure that you understand some classic mistakes that can be made, and we just avoid them. One of the things is, remember, the interaction volume is 2 microns. So I've seen some people do what's called a line scan. It's like a one-dimensional map. You just do a series of points in a particular direction, and it's looking for a diffusion profile, and you get the elemental concentration at each one of those points, and you plot a diffusion profile. But consider the interface on the left. That is a crystallographically perfect interface. It's atomically perfect. Nonetheless, because the interaction volume is of the order of a micron or 2, the interaction volume slowly approaches the interface, crosses it, and then slowly fades away from the interface. It is easily misinterpreted as a diffusion profile. There's actually no diffusion there. What you've got is you're trying to measure an interface that's atomically flat and atomically perfect with an effective analytical probe that's 1 or 2 microns wide. And you'll never see something smaller than your interaction volume. So people can misinterpret that as a diffusion profile 1 or 2 microns wide. You can only measure diffusion profiles greater than the interaction volume. The other thing is specimen charging. We've seen this in an SEM. The specimen can build up a charge, and then the build-up of local charge can deflect the beam away, and it looks like the image is moving. In analysis, especially when you're doing a point analysis, you don't realise the beam is moving because the image you're looking at is a frozen image. And you could start off analysing one phase and the beam will drift into another phase. That's something you've got to be aware of. The other issue is, normally when something is charging, you coat it, and that's fine. But what that really does, if you stop and think about it, is most of the electrons stop at the bottom of the interaction volume. That's 1 or 2 microns deep. The conductive coating we're putting on top is actually at the surface. Any electrons that are deep within the specimen, what I call subsurface charging, in an insulator, do not reach the conductive coating you put on the surface, and as such, the coating doesn't help much to negate subsurface charging. The image looks better because the image is the electrons in the space above the charging, but the X-rays are generated below in the specimen, and you can have 2,000 or 3,000 volts of charging there that are affecting the quality of the analysis. Well, you think you have a 20 kV beam, but you might have 2,000 volts of negative subsurface charging. As the electron passes through the coating, it's de-accelerated by that minus 2 kV charging, and the beam is turned from a 20 kV beam into an 18 kV beam. That's subsurface charging. Where do you see that if that's happening? You see it in the Dwayne Hunt limit. So even if the specimen doesn't look like it's charging, check the Duane-Hunt limit. That lets you know if you've got subsurface charging. The thing about subsurface charging is the accelerating voltage you think you're using isn't your true accelerating voltage. It's called your landing energy. What can you do about it? Well, coat it, doesn't always help. Be aware of it, check the Duane-Hunt limit. In the probe, one of the techniques is we run like with like. I look at the Duane-Hunt limit of all my standards, and then I match the Duane-Hunt limit of my standards to the Duane-Hunt limit of my unknown materials. That's the advanced way of doing it. It might take me a day or two to investigate all my standards to find out which one is the best one to use. That's why microprobe analysis is so good, but why microprobe analysis is so difficult. You may literally spend days working out how to correctly perform the analysis. Microprobe is the next level up. We won't spend much time on it. Of course, if you've got a conductive specimen on the left, so the electrons flow to Earth, no problem. Non-conductive specimen like on the right, you coat it. But the coating mostly lands on the top. You've got to make sure the specimen has a path to Earth, so you might want to put some conductive tape down the side, or some conductive carbon paint. I always do the paint on the side first, and then I coat onto it to seal it in. That's the best way to do it. Always remember, you're throwing electrons at atoms. You want the atoms you measure to be the atoms of your specimen, not the atoms of the fingerprint you've put on top of your specimen. If you're holding your specimen with your hand, there's finger grease there. Keep it clean, rinse it in ethanol, handle it with gloves, keep your gloves clean. Nothing much to say here, except on the left is what microanalysis is all about. We can analyse a material that's a few microns in size. On the right, that's a nice material there, but there's no one point I can analyse that gives me a representative analysis of the material. It just averages things badly. The right is called nanoanalysis, and I can't really do it easily in the SEM with a bulk specimen. What you have to do is you have to use a thin specimen, which is traditionally done in the TEM, the transmission electron microscope, but it can also be done in the SEM, and we'll just talk only a little bit about this. Now, before we investigate thin specimens, just to recap on why nanoanalysis is not possible in the SEM with a bulk specimen. This is a nice specimen. It's gallium arsenide nanowires. It's a base of pure gallium arsenide. It's seeded with pure gold crystals, which are nanometers across, and then from the gold crystals, nanowires grow, which are also gallium arsenide. On the left is secondary, and on the right is backscatter. And you can see those bright regions in backscatter on the right, that's my gold particles. I know they are pure gold. And I know that everything else is pure gallium arsenide, GaAs. Magnification, 70,000 times. Scale bar, 100 nanometers. I can easily see them in the SEM. In this case, backscatter is giving me good resolution because there's no information below the surface. It's a single crystal of pure gallium arsenide. When I put the spot to be analysed on what I know to be a pure gold particle, as you can see on the left, that's my spectra on the right. The spectra of my pure gold particle shows a little bit of gold and a lot of gallium and arsenic, because my gold particle is tens of nanometers in size, but my interaction volume is microns in size. And so what you're doing is you're averaging over the whole volume, of which the particle of interest is only a small proportion of the actual interaction volume. How do you do nanoanalysis? Well, you traditionally do it in the TEM, the transmission electron microscope, and step one is to remove most of the specimen, because as the electron beam hits the specimen, it begins to scatter. So we make a very, very thin specimen. How thin? Usually 10 to 100 nanometers thin. And then it's called electron transparent because the electron beam goes through the specimen. It's for materials where you need to investigate the fine structure such that the structure in some dimensions is smaller than the interaction volume of the bulk material. We use special corrections in the TEM matrix corrections because the standard SEM ZAF corrections no longer apply because things like volume effect and absorption effect have changed significantly in a thin specimen. We still use corrections, different type. On the left, you can see some typical TEM grids. They come in many different patterns, made out of different materials, and typically we use 3mm copper grids. Top right, that's where the copper grids go in the TEM, the transmission electron microscope. However, bottom right, that's an SEM pin stub, which you can purchase, and you can mount that pin stub in the SEM and you unscrew it and you can deposit 4 TEM grids into it. Underneath, because it's mounted high, underneath it is nothing. Normally I mount it over something with carbon in it to absorb any stray X-rays and electrons. But you can mount TEM samples, thin samples in the SEM. That's quite possible. And here's some work I did myself. This is a material where I needed to analyse very small submicron regions by getting a fibbed section made for a TEM, and then I mounted it in the SEM just like I described to you. I was able to analyse all those regions. You can see my analysis region as those little white dots. What are those white dots? Carbon contamination. Remember, there's always a carbon contamination in any electron microscope, and so you can never really quantify carbon. But that allowed me to analyse those different phases at submicron resolution. I calculated that the volume of analysis was about 100 nanometers in all dimensions. How good is it, you ask? You only know how good something is by putting in a known material and measuring it as an unknown. Again, I used a NIST standard reference material, an 1155 stainless steel. Let's have a look at it. Chromium, the reference value is 18.37. When I did it experimentally, 20 kV EDS as a thin foil, I got 18.45 weight percent with an error of 0.3. That's very good. So, I mean, that's an excellent result for chrome. You can see every element is unique. The chrome's pretty good. The iron is out by 1%, which is more than my reproducibility. And the moly is really out by a bit more than that. So again, I think that's a good result, but it's certainly not a perfect result. It just depends on how much effort you want to put into keeping on nursing the corrections. I didn't run standards. I used a standard calibration. If I ran my own standards, I could have improved that. But then I would have had to make multiple TEM specimens of multiple different elements and try to make sure that they were all the same thickness. You can do it. It's a difficult and long-winded process. And this is something I did a long, long time ago on what is now considered an ancient machine that doesn't even exist in the lab, a Lab 6 SEM. So you can certainly do a lot better now on a modern field emission SEM. 40,000 times, that's a small particle. I mounted TEM style, and in particular, I knew those particles had iron in it, but the question was, is the iron uniform or localized? The whole particle is only 1 or 2 microns across, and it's certainly probably less than a micron thick. By mapping for iron as a thin specimen, I can actually see that the iron grains are quite heavily localized, and some of those grains are only tens of nanometers across. This is work I did more than a decade ago. You could easily do better with a modern machine, but again, the limitations is really the machine. It's thinking through the physics of the process.